Continuing our trig tips here, this is the second part of the previous video, so some by hand methods for trig functions, and we are still, if we go back to what we did last time, we still need to find parameters c and b for our function. And just to jog your memory, this is actually the basically the screenshot of the previous video here, and we use the data you can see on the left of your screen. We used regression, courtesy of Desmos, trig regression, and you can see that we got a function with some parameters. We then got to work to do a by hand, more mathematical, analytical type approach. Because of the nature of the tidal creek data, it is not consistent in its peaks and troughs, at least not at every peak and not at every trough. So despite that, we formulated an approach. The approach we formulated treats all of the peaks as equals and all of the troughs as equals, and we'll see whether that gives us a good result. Now, mathematical modeling is messy, and it does require us to formulate and solve, evaluate and verify, check it out, and repeat those steps if what we come up with is a dud, or if it could be improved a bit more. Okay, dud's a bit extreme, but things like that do happen. Mathematical modeling is messy. So you can see on the screen that's our value we got for D, our value we got for A. Go back to that video if you want more of an insight on how we did that. Looking for C and B now. So C is your phase shift or your horizontal translation, and B is linked to the period. So let's move on then to find C. We're going to look at the average distance. We're talking about distance is a loose term, but how far across the x-axis on average do we have to go to get to a peak, to a trough, to another peak, to another trough, and so on. I'm going to refer to those as extremes. Okay, so how, on average, how far is it from extreme to extreme? So looking at the data, we've got, we're interested in this column here. So the first one we're going to do is go 12.35 minus 6.15. And actually, if you do that, that comes out as 6.2. Then we're going to look at the next pairing, and that would be 18.03 minus 12.35. And then if we do that, we get 5.68. And so on till we get to the bottom. And then we're going to divide by 10, because there's 10 jumps, 10 of those pairs, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. It's 11 data, but there's 10 jumps. Okay, so 10 gaps, 10 lots of x distance. Let's do the calculation. So I've just shown a sample of the calculations here, and to speed things up, I've gone ahead and done some of these. So those gaps I showed just above, alright, you can see on the left there, the green and the purple, I've shown them as calculations down here, and the results of those in red, and that goes on, and if you add all those amounts up, you get 61.7, and as I said, there are 10 of those, so what we need to do then is to get the average, we divide by how many, which is 10, so 61.7 over 10, and we get an average of 6.17 units. So once we divide by 10, we've got 6.17 units on average between each extreme, from peak to trough to peak to trough. Now you can use a cosine graph, but because we've settled with sine, we'd like to try and model the phase shift based on sine. And as you know, when sine starts, if you look at a basic sine graph, a sine graph without any transformations on it looks a bit like that. And so we've got something that has been shifted sideways, we suspect, because the first, basically the peak, so this sort of set up for a standard trig graph, sketch there. On our trig graph for this particular situation, we seem to have our first peak here at 6.15 along the x-axis. So let's say that's about there. That's at 6.15. And at 6.17 units either side we have another extreme. So if we went backwards this way before the data, we would get our next extreme there. Whoops, that's a bit rough, sorry. So you'll just have to ignore the shaggy bits off there. But just past there, because it's 6.17 either way, if we go by the average, and if that's 6.17, it's just gone past, so it'll be there at negative 0.02 on the x-axis. Normally on a standard sine graph we have this sort of phenomenon here. So we've got an apparent C value, definitely, and we normally have the midpoint here. Now because sine waves are generated from a unit circle, as we go around the unit circle we see, if we're using sine, which is the vertical component from our previous work, as the radius arm swings around, the distance it takes, or the angle it takes to go from the rest position, which would be here on the standard graph, to the max, is the same angle or x distance as it takes to get back to the next rest position, then down to a minimum, and so on. So that's a type of symmetry, or a type of equal wave distribution. So what would normally be here at this midpoint, okay, which would be like there, that rest point there, because the graph gets higher and the graph gets lower for sine beyond that. We don't have that there at 0, 0. We have that over here somewhere, because we know that it's moved, because instead of our pre-trough being down here, it's quite near the x. It's quite near the 0 on the x. The x value is nearly 0. It's only negative 0.02. So it's 0.02 to the left. Clearly we need to take another midpoint here, if it is a trig graph, to get an idea of where this would be. So that comes from basically assuming that it's a trig graph, which is a big assumption we're making here. So we're looking at basically the distance between there and there. We're assuming that, just like for trig graph, it's halfway. So we look at the difference between, and it's 6.17, that distance on this, using the averages. So we go 6.17 divided by 2. The halfway mark is 3.09. Sorry, 3.07. So we got that by halving the 6.17 average, and that value we got, we subtracted. So that half of 6.17 subtracted from 6.15 gave us 3.07. So basically the 3.07 on a standard trig graph would be happening, that point that's got that label on it, on our graph here, that would normally be happening 3.07 units to the left of that. So this has been shifted to the right. It's got a right, it's got a right phase shift, or it's been translated to the right. Okay, and that means we know what our C value, or at least our estimate of a good C value, might be. So we've basically got C equals negative 3.07, which will turn that part of the model that you should be familiar with into x minus 3.07. So now let's look at B, and parameter B is related to the period or the wavelength. From our previous work, B is 360 over the period, or 2 pi over the period if you're working in radians. So B in a sense is telling us how many periods fit inside 360 degrees, or how many periods fit inside 2 pi radians. So if our theme of averages as our method, we're looking at the average of the x distances between corresponding points. Alright, now what are corresponding points? It could be peak to peak, trough to trough. If you're really good, you'll do both. Okay, so if we're going to look at, I'll just look at peak to peak, but there is a better way of doing this if you go trough to trough or midpoint to midpoint from one cycle to the next cycle. So if you're looking at the data above, okay, now peak to peak first occurs here from there to there. So that's a peak and that's a peak, and that's the distance between, so it's 18.03 minus 6.15, which is 11.88. Alright, and you're finding the average of all of those. So from there to there, then from there to back to there, so 31.07 minus 18.03, see how they're both peaks? 42.98 minus 31.07, they're both peaks, and so on. Another thing you could try is the high peaks to the high peaks. Check that out, but you'll have to think it through a bit more differently. So in the last peak to peak is from there back to there. You need to average those out. So you've got 1 pair, 2 pairs, 3 pairs, 4 pairs, 5 pairs. So you sum those amounts up and divide by 5, because there's 5 pairings. So I did those just based on peaks only, but you might want to investigate a bit more closely. I get 61.7, which should ring sort of a bell, because back here we got 61.7 as well, the averages between each extreme. That suggests there's a bit of consistency. And 12.34 is the average from there to there. So what does that mean? Well, based on that bit of data, it means that on average the peaks are 12.34 apart, and that fits in with the decimal of the definition of a period, doesn't it? So we've got a period is approximately equal to 12.34 based on the data we used and based on using peaks only. For your data, you may wish to look, if it's not as consistent, you may wish to look deeper, factor in trough to trough as well, and put all the averages together, divide by 10 if you've got 5 peaks and 5 gaps between peaks and 5 gaps between troughs. You might have an average based on 10, which might, for your data, may be better, maybe not. Doesn't look like it's going to be any better for this data. So you've got 12.34. So we're in this particular problem, we're working in degrees, so B equals 360 over 12.34, and that is 29.17. So now we've got A, B, C and D, and I've put those into Desmos, and I've got the other graph from the green graph is from the trigonomic regression from the previous video, and this is the new one up here. Alright, and I've got all the data in there as well. So just leaving only the manufacturer graph, you need to check and evaluate the validity of it and verify how good it is. If not, you may need to go back. Alright, now if you need to go back, remember you've got formulate, solve, evaluate and verify. And remember, the process is if it comes out of there and is it suitable? All right. If it's not suitable, well, a good student who wants to get a good grade will go back, and you may need to check your formulate stage, assumptions and observations, and the data you've chosen to use, and the original regression formula, and then resolve where necessary, and then retry that. So it's an iterative cycling thing to get. That's the checking point there. So that's, you'll be able to determine how well you're going. If you don't do well on the first thing, don't delete it. Keep that. I want to see the story of it. One way to evaluate and verify, here's a little trick. If you put an x equals line in there on a slider bar, you can line it up. So we've got a data value here, which was one of our data values. Okay, it's this one here. Alright, and basically you can check on that if you can get the slider bar onto it. And slider bars, you can fine tune it to make it go up in smaller steps. Okay, if you want to make it go up in hundredths, you do that, and basically you can just check it out. You can try and get the intersection points there. Okay, so it's about 31 there, and there's a slight difference in the readings. Now, what you should do with your regression graph is to use this process. So I should actually swap it around. With the by hand graph, you should use substitution. So you need to substitute in values for x using the by hand method, and you can use digital methods like this for the regressed line, like that. Okay, just by clicking on there. So you can see there's a bit of difference, and you should check it out for number of points. After that, once you've settled for a pretty good graph for the short term, you should then extend out to the long term by looking further out. Okay, now graphically you do it like that. Okay, and algebraically you sub in values for x, which is your time, that correspond with these much longer time scales, and just check it, and you'll be able to identify whether the best model you've been able to create is good or bad